The universe is a place of profound silence. If we were to float in the space between the stars, far from the interference of our own sun and the noise of our own civilization, we would be enveloped by a quiet so absolute it would feel heavy. It is a vacuum, a vast expanse where sound cannot travel, where the great, violent events of the cosmos, the collision of galaxies, the birth of stars, the supernova explosions, play out in a silence that feels almost respectful of the magnitude of the events. For most of human history, we looked up at the night canvas and saw only points of light. We called them the fixed stars. They were the reliable narrators of our seasons, the navigational beacons for our ships, and the mythological characters of our stories. They appeared to us as static, unchanging, and eternal. They were perfect, unblemished diamonds sewn into a velvet curtain that wrapped around our world. We believed, for thousands of years, that we were the only place that possessed the chaotic beauty of weather. We felt the rain on our skin, watched the lightning tear through the violet clouds of a summer storm, and shivered in the snow. We assumed that out there in the deep black, the stars were merely burning fires, and if there were other worlds, they were too far, too small, and too hidden to ever be known to us. But the light that reaches us is not static. If you lie on your back on a grassy hill on a clear, moonless night and let your eyes adjust to the darkness, you will see the stars twinkling. We know now that this twinkling is an atmospheric trick, a distortion caused by the layers of air above our heads. But in a poetic sense, that wavering light was trying to tell us something. It was telling us that the universe is not still. It is dynamic. It is in motion. To understand the storms on a world light years away, we must first understand the journey of the light itself. Imagine a photon, a single packet of light, born in the crushing nuclear furnace of a distant star. It fights its way out of the star's core, a process that can take tens of thousands of years, bouncing and scattering until it finally breaks the surface and rushes out into the void. It travels for centuries or perhaps millennia. It passes through clouds of interstellar dust. It dodges the gravitational pull of dark planets, and it crosses the freezing emptiness of the spiral arms of the galaxy. Finally, it arrives here. It strikes the mirror of a telescope. It is captured. And within that tiny, ancient packet of light carries a secret. It carries the signature of what it passed through. If that light skimmed the edge of a planet on its way to us, it picked up a fingerprint. It picked up the memory of wind, of heat, of clouds. For decades, astronomers dreamed of reading these memories. But the stars are so bright, and the planets that orbit them are so dim, that it is like trying to spot a firefly hovering next to a searchlight while standing on a different continent. The glare washes everything out. The planets were lost in the brilliance of their parents. We found them, eventually, not by seeing them directly, but by seeing how they tugged on their stars, or how they dimmed the light when they passed in front. We found them as shadows. We found them as math. We knew they were there. We named them with strings of numbers and letters. HD 209458B, WASP 76B, VHS 1256B. They were catalogued. We knew their mass. We knew how long their year was. We knew if they were hot or cold. But they remained, in our minds, as spheres of geometry. We could calculate their gravity, but we could not imagine standing on their surface. We could not imagine the wind. The atmosphere of a planet is its breath. It is the thin, fragile layer that mediates between the rock of the world and the harshness of space. It is where the drama happens. On Earth, our atmosphere is a chaotic engine driven by the heat of the sun and the rotation of the globe. It creates hurricanes that spiral like galaxies. It creates gentle breezes that scatter pollen. It creates the heavy grey blankets of winter clouds. Atmosphere is what makes a planet feel alive. A rock without an atmosphere is a tomb preserved in vacuum. But a world with air, with clouds, with movement, that is a world with a story. To find storms on these alien worlds, we needed to move beyond the simple detection of the planet's existence. We needed to stop asking, is it there? And start asking, what is it like? This required a shift in our technology and our perspective. We needed to peel apart the light. We needed to look not at the brightness of the star, but at the spectrum of the colors. When light passes through a prism, it breaks into a rainbow. This is spectroscopy. If you pass sunlight through a prism, you see the colors of the rainbow, but if you look closely, very closely, there are dark lines missing from the spectrum. These are absorption lines. They are caused by elements in the sun's atmosphere absorbing specific wavelengths of light: hydrogen, helium, sodium. They all leave a unique barcode in the rainbow. Now, imagine doing this for a planet hundreds of light years away. Imagine waiting for that planet to pass in front of its star. As the planet crosses the face of the sun, a tiny fraction of the starlight filters through the rim of the planet's atmosphere. It passes through the alien air before continuing on its journey to Earth. If there are clouds on that planet, they block the light. If there is water vapor, it absorbs the red light. If there is methane, it absorbs the blue. By analyzing the light that survives the passage through the alien sky, we can reconstruct the atmosphere. We can taste the air of a world we will never visit. But ground-based telescopes are limited. They must look through Earth's own turbulent, watery atmosphere to see the subtle signs of weather on a distant world, to see the rise and fall of global winds, the swirling of grit and sand in an alien sky. We needed to rise above our own air. We needed an eye in the void. We needed a mirror that was cold, stable, and incredibly precise. We needed a time machine. We needed a giant, golden observatory that could sit in the eternal shadow of the Earth and watch the infrared universe with unblinking focus. This was the dream that would become the James Webb Space Telescope, and it was this machine that would finally confirm that the universe is not just filled with rocks and gas, but with storms of unimaginable power. The construction of the eye that would see these storms was, in itself, a journey of patience and precision. The James Webb Space Telescope is not merely a camera, it is a monument to human curiosity. It is the most complex observatory ever built, a collection of 18 hexagonal segments of beryllium coated in a microscopic layer of pure gold. Gold is the metal of choice not for its vanity, but for its physics. It is the perfect reflector of infrared light. Infrared is the language of heat. The visible light that our eyes can see is only a tiny fraction of the electromagnetic spectrum. But the universe is filled with things that do not glow in visible light. There are clouds of dust, cold stars, and distant galaxies that are red-shifted by the expansion of space. And, crucially for our story, there are the thermal signatures of planets. Planets are warm, even the coldest ones emit a faint heat signature. Storms, clouds, and atmospheric currents are fundamentally engines of heat distribution. On Earth, a storm is simply the atmosphere trying to move heat from a warm place to a cold place. By looking at the universe in infrared, we are looking at the movement of energy. We are watching the heat of a planet pulse and flow. The James Webb Space Telescope was sent to a place called Lagrange Point 2, or L2. This is a point of gravitational balance, 1,000,000 miles away from Earth, on the side opposite the Sun. Here, the telescope can stay in a fixed position relative to the Earth and the Sun. It keeps its back to the heat. It unfolds a sun shield the size of a tennis court, 5 layers of captain that separate the observatory into a hot side and a cold side. On the hot side, the sun beats down, heating the shield to temperatures hot enough to boil water. On the cold side, where the golden mirrors sit, the temperature plunges to near absolute zero. In this profound cold, the telescope can sense the faintest whisper of heat from the deep universe. It is so sensitive that it could detect the heat of a bumblebee hovering at the distance of the moon. When the telescope opened its eyes, the data began to flow. It did not come as a photograph, not in the way we are used to seeing. It came as graphs, as jagged lines on a chart, as streams of numbers. To the untrained eye, it looked like static. But to the planetary scientists, it was a symphony. They turned this golden eye towards specific targets. They looked at worlds that we had known about for years but had never truly seen. They looked at hot Jupiters, gas giants that orbit so close to their stars that their years last only days. They looked at super-Earths and sub-Neptunes. and they looked at a class of objects that blur the line between star and planet: brown dwarfs. One of the most remarkable things about observing exoplanet weather is that we are observing a global phenomenon all at once. When we look at weather on Earth, we are usually standing inside it or looking at a satellite map of the specific region. But when JWST looks at an exoplanet, it sees the integrated light of the entire hemisphere. The confirmation of storms did not come from seeing a spiral shape like a hurricane. We cannot resolve the surface of these planets that clearly they are too far away. Instead, the confirmation came from change. It came from variability. The astronomers watched the light curve of the planet. They watched the brightness of the infrared signal over time. If a planet has a clear, static atmosphere, the heat signature should be relatively constant as the planet rotates, predictable and smooth. But that is not what they saw. On the planet designated VHS 1256b and others like JWST 43b, the light curve was restless. It rose and fell in complex patterns. It shimmered. This variability meant that the face of the planet was changing as it rotated. It meant that something was blocking the heat, then revealing it, then blocking it again. It meant clouds. But these were not clouds of water vapor like the cumulus towers that drift over the Atlantic Ocean. The chemistry of these worlds is far more exotic. The spectroscopic data, the rainbow fingerprint, revealed lines that corresponded to silicates. Rock. The clouds on these worlds are made of hot sand. They are made of smoke and minerals. Imagine a cloud system where the vapor is not water, but vaporized rock, condensing in the upper atmosphere to form grains of enstatite or quartz. As the planet rotates, huge banks of these silicate clouds, massive distinct weather systems, sweep across the face of the world. The telescope saw the brightening as a hole in the clouds rotated into view, letting the intense heat from the deeper layers escape. Then it saw the dimming as a thick bank of high-altitude grit swept over the area, trapping the heat and muting the signal. This rising and falling of light was the heartbeat of a storm. This was the moment of confirmation. We were no longer inferring that atmosphere existed. We were watching the weather forecast of a world 40 light-years away. We were seeing the dynamics of an alien climate system in real time. The realization is humbling. We often think of space as empty and static, but these data points prove that the galaxy is filled with turbulence. Every dot of light in the sky is potentially a sun to a world that is raging with activity. There are winds blowing at thousands of miles per hour. There are clouds of ruby and sapphire dust. There are rains of molten iron. The silence of the vacuum is an illusion. If we could hear the radio waves, if we could hear the turbulence of magnetic fields and the roar of planetary winds, the universe would be a cacophony. But because we rely on light, and specifically now on the infrared light collected by our golden mirror at L2, we see it as a beautiful rhythmic pulsing. We have begun the era of exoplanet meteorology. We are no longer just map makers of the stars, we are becoming weather watchers of the galaxy. And as we drift deeper into this specific example, the world of VHS 1256b, we begin to understand just how violent, beautiful, and utterly alien these storms can be. We have to let go of our Earth-centric view of what weather means. We have to expand our imagination to accept a reality where the air itself burns and the clouds are heavier than stone. Let us drift now, in our mind's eye, away from the safe harbor of Earth. Let us move past the orbit of Mars, past the giants of Jupiter and Saturn, and leave our solar system behind. We are traveling on the stream of data provided by the James Webb Space Telescope. We are heading toward a specific point in the constellation of Corvus, the Raven. We are going to visit a world that has no sun, a world that glows with its own dying heat, and a world where the storm never ends. We arrive now at the object of our fascination. In the catalogue of the cosmos, it is known as VHS 1256b. It is a name that sounds like a machine part, a serial number filed away in a dusty drawer of astrophysics. But names are often deceptive. They are dry labels for things that are, in reality, majestic and terrifying. VHS 156b is located about 40 light-years from Earth. In the grand scale of the galaxy, this is our backyard. It is a neighbor. But it is a neighbor that lives in a house we would struggle to recognize. This world is not hugging its parent star in a tight, frantic orbit like many of the hot Jupiters we have discovered. It wanders far out, at a distance 4 times greater than Pluto is from our Sun. It orbits a pair of small red stars, but it is so distant from them that their light is merely a bright double star in its sky, not a dominating sun. Because it is so far away from the blinding glare of its parents, it was a perfect target for the James Webb Space Telescope. The telescope did not have to squint. It could stare directly at the planet. It could open its shutter and drink in the light that the planet itself was emitting. And this is the first thing we must understand about this world. It glows. It is young. In cosmic terms, it is an infant, perhaps only 150 million years old. It has not yet had time to cool down from the violence of its formation. It is still contracting, gravity pulling its mass inward, squeezing the core and generating immense heat. The surface temperature is over 1,500 degrees Fahrenheit. It is hot enough to melt aluminum. It is hot enough to soften glass. If we were to drift toward it, moving through the silence of interstellar space, we would not see a blue marble like Earth, nor a banded yellow giant like Saturn. We would see a dark, reddish ember. It would glow with a dull, malevolent light like a coal left in a dying fire. It is a world suspended in eternal twilight, lit not by a sun from above, but by the furnace from within. As we descend toward the atmosphere, the details begin to resolve. And this is where the James Webb Space Telescope changed everything. Before Webb, we might have guessed at the composition of the atmosphere. We might have assumed it was thick with hydrogen and helium, simple and clear. But the telescope's spectrograph, the instrument that breaks light into rainbows, saw something distinct. It saw the signature of silicate grains. Silicate is the stuff of rocks. It is the stuff of sand, of quartz, of feldspar. It is the material that makes up the beaches of Earth and the glass in our windows. On our world, rock is solid. It sits on the ground. It is heavy, immovable and cold. But on VHS 156b, the rock is in the sky. The atmosphere is a swirling, chaotic soup of vaporized minerals. The heat is so intense deep down that rock turns to gas. It rises, carried by massive convection currents that dwarf any hurricane on Earth. As this vaporized rock rises higher, the pressure drops and the temperature cools. And just as water vapor on Earth condenses into liquid droplets to form clouds, the rock vapor on this alien world condenses. But it does not condense into water. It condenses into dust. It condenses into tiny microscopic grains of hot sand. Imagine a cloud deck that stretches from pole to pole, but the clouds are not made of water vapor. They are made of smoke and grit. They are clouds of enstite and forsterite. They are heavy, opaque, and dense. These are not the white, fluffy clouds of a summer afternoon. They are dark clouds, perhaps brownish red or silty grey, glowing faintly from the heat beneath them. The telescope saw that these clouds are not a uniform blanket. They are broken. They are patchy. There are clearer regions where the heat from the deep interior shines through brightly, and there are thick, towering banks of silicate clouds that block the light. This patchiness is what caused the flickering light curve the astronomers observed. As the planet rotates, a day on this world lasts about 22 hours. The brighter, clearer spots rotate out of view, and the darker, cooler cloud banks rotate in. The planet blinks. It pulses. We are looking at a storm system that covers the entire world. It is a global, turbulent ocean of gas and dust. The winds here are likely moving at hundreds of miles per hour, whipping the silicate grains around the planet in vast bands. The friction between these grains, the rubbing of sand against sand in the upper atmosphere, would generate static electricity on a scale we can barely comprehend. If we could stand on a floating platform in the upper atmosphere of VHS 1256b, the view would be overwhelming. Above us, the blackness of space, perhaps starry, perhaps obscured by high-altitude haze. Below us, a churning sea of clouds. but these clouds would be glowing. The troughs between the waves of clouds would shine with the deep red light of the planet's internal fire. The peaks of the clouds would be dark silhouettes against the glow. And every now and then, the sky would be torn apart by lightning. Not the blue-white snap of Earth lightning, but perhaps discharge across thousands of miles, illuminating the swirling dust from within. The thunder would be a continuous rolling roar, a bass note that vibrates through the thick atmosphere, never ceasing, never fading. This is the reality of the data. The James Webb Space Telescope detected water, methane, carbon monoxide, and carbon dioxide. It detected sodium and potassium. But the crowning discovery, the one that confirmed the violent nature of this world, was the dust, the sand. It is a world where the very air is gritty. It is a world of constant abrasion. It is a world that is essentially a self-luminous, sandstorm-covered sphere floating alone in the dark. And yet, this terrifying environment is governed by the same laws of physics that govern a gentle rain shower in a garden on Earth. It is the same process, played out with different ingredients, at a different temperature. It is the universality of nature. The storm on VHS 1256b is not an anomaly. It is likely the standard for worlds like this. Brown dwarfs. Objects that bridge the gap between stars and planets are famous for their weather. They are too massive to be planets, but not massive enough to ignite nuclear fusion and become stars. They are failed stars, cooling slowly over billions of years. And in that cooling process, they develop atmospheres of incredible complexity. Webb's observation of this specific world was the most detailed look we have ever had at such a place. It was a spectrum of the highest fidelity. It allowed us to peel back the layers. We saw the top of the atmosphere where it is thinner. We saw the deeper layers where the pressure builds. We saw the mixing. We saw that the atmosphere is not stagnant, it is boiling. This vertical movement, this mixing, is the engine of the storm. It brings the chemically rich air from the deep, hot interior up to the surface. It drags the cool, sandy clouds down into the depths to be melted again. It is a cycle, a rock cycle, but one that happens in the air, not on the ground. On Earth, the rock cycle takes millions of years. Rocks erode, become sediment, get buried, melt into magma, and erupt from volcanoes. On VHS 1256b, the rock cycle happens every few hours. Rock becomes gas, becomes cloud, becomes rain, becomes gas again. The planet is recycling itself in a frantic eternal loop. To witness this, even through the data of a telescope, is to witness the dynamism of the universe. It reminds us that solid is a relative term. Rock is only solid because we live in a cold place. Heat it up and it flows like water. Heat it up more and it floats like a cloud. The universe does not care about our definitions of solid, liquid, or gas. It only cares about temperature and pressure. And on the stormy world of VHS 1256b, the definitions are fluid. To truly appreciate the magnitude of these storms, we must slow down and understand the architecture of an atmosphere. We must visualize the sky not as a single layer, but as a ladder. An atmosphere is a structure built of gas, held together by gravity and organized by heat. On Earth, we are familiar with this ladder. We live on the bottom rung, the troposphere. This is where the weather happens. It is where the air is thickest, where the clouds form, where the birds fly. Above that is the stratosphere, a calm, dry layer where the ozone sits. Above that, the mesosphere, the thermosphere, and finally the exosphere, fading gently into space. On a giant exoplanet or a brown dwarf like VHS 1256b, the ladder is much taller. The gravity is stronger, pulling the gas tight against the core, but the heat puffs it out, expanding it into a vast envelope. The bottom of this atmosphere is not a solid surface. There is no ground to stand on. If you were to fall through the clouds, you would not hit rock. You would simply sink deeper and deeper into the gloom. The gas would become thicker, turning into a hot, dense fog, then a soup-like fluid, and finally a metallic liquid ocean of hydrogen thousands of miles deep. The storms confirmed by the James Webb Space Telescope are phenomena of the upper atmosphere, the part of the ladder that interacts with space. This is the photosphere of the planet, the sphere of light. It is the skin. The mechanism driving the storm is convection. We can see this in a pot of boiling oatmeal. Bubbles of hot material rise from the bottom, burst at the surface, and the cooler material sinks back down at the edges. This is exactly what is happening on VHS 156b, but on a planetary scale. The core of the planet is the heat source. Parcels of gas deep inside become buoyant. They are hotter than their surroundings, so they rise. As they rise, they expand. As they expand, they cool. This is a fundamental rule of thermodynamics. Expansion causes cooling. As this rising column of gas cools, the chemicals inside it begin to change state. Deep down, the silicates, the rock, are vapor. They are invisible gas, just as water vapor is invisible in hot air. But as the gas rises to the cooler upper altitudes, it crosses a threshold. It hits the dew point, but for rock. Suddenly the vapor can no longer stay a gas. It precipitates. Atoms of silicon and oxygen snap together, locking into crystal lattices. In an instant, a clear gas becomes a cloud of solid particles. This is the birth of the silicate cloud. But the story does not end with the formation of the cloud. The particles grow, they bump into each other, they stick together, they form larger grains. And eventually, they become too heavy to be supported by the updraft of the gas. Gravity asserts its dominance, and so it begins to rain. The rain on VHS 1256b is a subject of intense scientific curiosity and poetic wonder. It is not a rain of liquid drops, it is a rain of sand, or perhaps, depending on the temperature, a rain of molten pebbles. Imagine a rainstorm of hot, microscopic jewels. As these particles fall, they leave the cool upper atmosphere and drop back down into the hellish depths. As they descend, the temperature rises. The ladder gets hotter as you go down. Eventually, the falling sand hits a layer where the heat is intense enough to melt it and then vaporize it. The rain evaporates before it ever hits the bottom. The cloud turns back into gas. The rock returns to the vapor state, ready to be heated, lifted, and recycled once again. This creates a vertical circulation. Updrafts of clear gas, downdrafts of sandy rain. This vertical movement is what mixes the atmosphere. It churns the chemicals. It ensures that the carbon monoxide and the methane and the water are constantly moving, constantly interacting. The James Webb Telescope can see this mixing. When astronomers look at the spectrum, they see chemicals that shouldn't be there if the air was still. They see gases that belong in the deep hot layers floating in the upper, cool layers. This is proof of the dredging motion of the storms. The planet is turning itself inside out over and over again. And then there are the horizontal winds. Because the planet is rotating, spinning on its axis every 22 hours, the atmosphere is dragged along. But fluids on a rotating sphere behave in complex ways. The Coriolis effect, the force that makes hurricanes spin, twists the winds. It creates bands. It creates jets. On Jupiter, we see these bands as stripes of white and red. On VHS 156b, we expect similar banding but clearer and more violent due to the heat. There are likely jet streams, rivers of fast-moving air that encircle the planet, acting as barriers between different climate zones. Inside these jet streams, vortices form. Eddies. Whirlpools of gas the size of Earth. These are the storms. These are the great red spots of the brown dwarf. They are high-pressure systems where the clouds are pushed high up, towering over the surroundings. The silence of the observation contrasts with the violence of the reality. When we look at the data from Webb, we see a wiggly line on a graph, a dip in brightness, a spike in a wavelength. It looks sterile. It looks mathematical. But that wiggly line represents a tempest of unimaginable energy. It represents 1 billion tons of hot sand screaming through a hydrogen sky. It represents the universe doing what it does best, transforming energy. The storm is just a machine for moving heat. It is the planet trying to find equilibrium, trying to balance the hot interior with the cold vacuum of space. The beauty is in the struggle. The planet will never find that balance, not for billions of years. And so, the storm rages on. We are witnessing the fluid dynamics of the cosmos. Whether it is the milk swirling in a coffee cup, the clouds drifting over a mountain range, or the silicate storms of a distant world, the physics are the same. We are connected to these alien worlds by the laws of nature. We can understand them because we share the same reality. The James Webb Space Telescope has given us the eyes to see this connection. It has allowed us to look at a point of light and say, there is wind there is rain there is change. It has turned a static universe into a dynamic one. And as we continue to stare into the infrared, we find that VHS 1256b is not alone. It is merely the clearest example, the Rosetta Stone that is teaching us how to read the weather of the galaxy. There are other worlds, other storms, waiting in the dark. To understand the true nature of a storm on a world 40 light-years away, we must look beyond the simple concept of wind. Wind is merely the vehicle, the cargo is chemistry. When the James Webb Space Telescope turned its golden mirror toward VHS 1256b, it did not just see the movement of clouds or the flickering of heat. It tasted the air. It performed a chemical inventory of an alien atmosphere, and what it found was a chaotic, beautiful mixture that tells the story of a planet in constant turmoil. The data that Webb returned came in the form of a spectrum. To the uninitiated, a spectrum looks like a jagged line on a graph, a series of peaks and valleys mapped against wavelengths of light. But to an astronomer, that jagged line is a narrative. It is a code that, when broken, reveals the molecular fingerprint of the universe. It showed us that the storms on this world are not just moving heat, they are moving molecules. They are churning the very ingredients of the cosmos in a planetary-sized mixer. Consider the water. The data revealed clear, unmistakable signatures of water vapor. But we must be careful with our imagery here. This is not the cool, refreshing water of a mountain stream, nor the gentle mist of a morning meadow. This is superheated steam. These are water molecules vibrating with intense thermal energy, floating in the upper atmosphere of a world that glows like a dying ember. The presence of water is profound because it connects this alien sphere to our own blue world. It reminds us that the universe uses the same building blocks everywhere. The hydrogen and oxygen that bond to create the oceans of Earth are the same hydrogen and oxygen that float in the burning skies of a brown dwarf. But the water was not alone. Alongside the steam, the telescope detected methane. And alongside the methane, it found carbon monoxide. In a calm, cool, settled atmosphere, these molecules tend to segregate. Methane prefers cooler temperatures and typically settles in the upper layers of cooler worlds. Carbon monoxide is robust. It prefers the heat and typically dominates in the deep, crushing warmth of the lower atmosphere. On a world that has had time to settle, we might expect to see layers, distinct and orderly, like oil floating on water. We might expect the chemistry to have reached a state of equilibrium, a balance where the reactions have stabilized. But VHS 1256b is not stable. It is in a state of chemical disequilibrium. This is a scientific way of saying that the atmosphere is restless. The telescope found methane and carbon monoxide mingling together in the same layers of the sky. This shouldn't happen if the air was still. The only way for these distinct chemical signatures to exist side by side in the quantities observed is if the atmosphere is being violently stirred. This observation serves as the smoking gun for the vertical nature of the storms. The deep, hot currents, updrafts of unimaginable power, are dredging up carbon monoxide from the interior, dragging it up into the cooler upper layers faster than it can chemically react and disappear. Simultaneously, the cooler methane from the upper clouds is being pushed down into the depths. The planet is breathing. It is exhaling the deep heat and inhaling the cool surface air in a cycle that never pauses. The detection of carbon dioxide adds another layer to this complexity. Carbon dioxide is a heavy molecule. Finding it lofted high in the atmosphere is further proof of the power of the winds. It is as if the planet is refusing to let its atmosphere settle. It is a world that is constantly remixing itself, ensuring that no single layer ever becomes stagnant. And then there are the alkalis, sodium and potassium. On Earth, we associate these with salt and nutrition. In the atmosphere of a star or a brown dwarf, they act as spectral absorbents. They eat light, they shape the color of the world. Because of these elements and the scattering of the silicate dust, the planet likely does not glow with the bright yellow of a sun, nor the reflected blue of Earth. It likely glows with a deep, moody magenta or a reddish-purple hue, a color born of cooling gas, heavy metals, and the scattering of light through clouds of rock. The sheer amount of data Webb collected from this single target allowed astronomers to see the shape of these molecules. They could see how the light was absorbed at different wavelengths, which tells us about the pressure of the gas. They could effectively see the altitude of the different chemical layers. They could build a 3D model of the atmosphere in their computers. What emerges is a picture of a world that is chemically rich but physically torturous. It is a laboratory where the experiments never end. The heat breaks molecules apart, the cooling allows them to reform. The wind mixes them, the gravity pulls them down. It is a cycle of destruction and creation that happens on a timescale of hours. We have spent our journey thus far in the realm of the extreme. We have stood in the mental landscape of VHS 1256b, watching clouds of hot sand swirl through a violet sky. We have witnessed the violence of a world that burns with the heat of its own creation. These worlds, the brown dwarfs, the hot Jupiters, are the first to reveal their secrets because they are loud. Their storms are massive, their heat is intense, and their signals roar across the vacuum. But the ambition of our species does not end with the discovery of monsters. The detection of silicate storms is a proof of concept. It is a signal that we have the technology to read the weather of the galaxy. And now, the eyes of the astronomers are turning towards something quieter, something fainter, something that might remind us of home. We are beginning the search for a gentle breeze. The James Webb Space Telescope, having cut its teeth on the giants, is now pushing the boundaries of what is possible by peering at rocky worlds. These are the planets that sit in the Goldilocks zone of their stars. Not too hot, not too cold. They are the worlds where water might sit as a liquid ocean, not as superheated steam or ice. Finding weather on these worlds is infinitely harder. The atmosphere of an Earth-sized planet is a thin, delicate skin compared to the bloated envelope of a gas giant. It blocks very little light. The signal is a whisper buried in the noise of the star. But the principles we learned from VHS 1256b still apply. If a rocky planet has weather, it has variability. If it has oceans, it has clouds. And if it has clouds, it has a changing face. Imagine a world in the TRAPPIST-1 system, a red dwarf star orbited by 7 rocky siblings. We turn our gaze to the 4th planet. We stare for hours, days, weeks. We are looking for the glint. On Earth, we call this sun glint, the reflection of sunlight off the smooth surface of the ocean. If we could detect a glint on an exoplanet, and if that glint appeared and disappeared, it would tell us about the weather. It would tell us that clouds are moving in front of the mirror. We are looking for the signature of a water cycle. Not the violent vertical dredging of a brown dwarf, but the horizontal cyclic flow of evaporation and rain. The discovery of a water cloud on a rocky world would be a moment of profound silence in the control room. It would be the discovery of a stage where life could potentially perform. Weather is the engine of biology. It distributes heat. It circulates nutrients. It scrubs the air. A planet without weather is a stagnant pool. A planet with weather is a flowing river. The future of this exploration involves looking for disequilibrium that cannot be explained by geology alone. On VHS 1076b, the disequilibrium was caused by vertical winds moving carbon monoxide. On a living world, the disequilibrium might be caused by life itself. Oxygen and methane do not like to exist together. They react and destroy each other. If we found an atmosphere rich in both, and if we saw that atmosphere changing, breathing with the seasons, it would be the strongest evidence yet that the planet is alive. We would be watching the metabolism of a biosphere through the movement of its air. The storms we found on the brown dwarf are the overture. They are the loud, brassy opening notes of a symphony. The weather on an Earth-like world is the quiet melody that follows. It requires more patience to hear. It requires us to stare into the darkness for longer. But the golden mirror is capable, and the next generation of telescopes, the giants currently being built on the mountaintops of Chile and Hawaii, will join the chorus. We are moving from the era of detection to the era of mapping. We are dreaming of the day when we can produce a weather map for a world we will never walk on. A map with high-pressure zones, cold fronts and trade winds. A map that might tell us, across the impossible distance, that it is a sunny day on Proxima Centauri b. As we reach the end of this exploration, we must step back from the specific data. The silicate grains, the methane absorption lines, the light curves, and consider the act of observation itself. There is a profound intimacy in the study of exoplanet weather. When a photon leaves the cloud deck of VHS 1256b, it travels for 40 years. It carries the energy of that specific storm, that specific moment of turbulence. It crosses the interstellar dark, a lonely messenger in a vast void. When it hits the mirror of the James Webb Space Telescope, that energy is absorbed. The photon dies. But in its death, it transfers its information to us. We convert it into an electron, then into a bit of data, then into a pixel on a screen, and finally, into a thought in a human mind. The storm that happened 40 years ago on a brown dwarf is now a storm happening in our imagination. We have reconstructed it. We have given it a second life. This connection changes us. For most of human existence, the sky was above us. It was a ceiling. Now, the sky is a depth. It is a three-dimensional sea that we are learning to navigate. We are no longer confined to the weather of Earth. We are citizens of a galaxy that is teeming with wind and rain. There is a concept in cosmology called the cosmic perspective. It is the realization of our smallness, but also of our connection. When we look at the violent, inhospitable storms of a world like VHS 1256b, we are reminded of the rarity of our own calm. Earth is a sanctuary. Our storms are governed by a delicate balance. Our atmosphere is a shield, not a shroud of burning sand. Seeing the ferocity of the universe should make us cherish the gentle rain of our own world. It should make us value the blue sky that protects us. But it also tells us that we are not the center of the story. The storms of VHS 1256b rage regardless of whether we see them. They churned for millions of years before we built a telescope, and they will churn for millions of years after we are gone. The universe is busy. It is occupied with its own business of energy transfer and entropy. We are the witnesses. We are the universe waking up to itself. We are the only part of the cosmos, as far as we know, that can look at a storm on another world and wonder why. The confirmation of these storms is a triumph of patience. It is the result of thousands of scientists, engineers, and dreamers who believed that if we polished a mirror smooth enough and folded it into a rocket and sent it 1,000,000 miles away, we could see the invisible. And they were right. The documentary of the universe is being written in real time. The script is the light, the narrator is the math, and the audience is us. As we close our eyes tonight here on the surface of our own spinning world, let us remember the other worlds. Let us remember the hot sandy clouds of the brown dwarfs. Let us remember the iron rain of the hot Jupiters. Let us remember the silent waiting atmospheres of the rocky planets. The dark is not empty. It is full of wind. It is full of heat. It is full of the echoes of 1,000,000,000 storms, blowing in the silence, waiting for us to turn our golden eye toward them and listen. We are the weather watchers of the Milky Way, and the forecast is infinite.